Bow, bow, bow. 2 minutes. 2. Good afternoon. What's up? All right, it's 12:30. Let's get started. Lord, thank you for bringing us together this afternoon. Thank you for everything that you do for us, for the promise of the weekend. Pray that you would continue to bless us, that you would help give us what we need to make it through the rest of the semester strongly and help us to be successful. In your name we pray. Amen. All right. We are the end of week 11. We're going to do some problems and stuff today. Well, I continue on stuff we did last class, right? There we go. Right. Let's see. I don't remember if anybody wrote that in, so let me go and pull it up. Sorry for not pulling it up before class. I keep forgetting that this computer doesn't link with Pull Everywhere, which, as you can tell, is super convenient. Okay. So here we are. This is the thing. All right, matrix gear ratio. I don't know why matrix came up. I think that's a holdover from maybe a different class, because we didn't talk anything about matrices in this class, and they're not going to come up, so I'm not going to talk about them. So if that's okay with you guys, we'll just talk about gear ratio, right? So what is gear ratio, right? So we all know that if you have like a really small gear rotating very quickly, right? And it's attached to a larger gear, the larger gear is going to have less angular velocity, right? It's going to rotate more slowly. This means that we transfer that speed, right? We're transferring power in a sense, right? So when we're talking about gear ratio, and here, let me put a slide in so we can kind of talk about it. Slide in. New slide. Okay. So if we wanted to talk about gear ratio, right? I've got two gears. Okay. Let's try that again. This time, I've got two gears, right? I've got this big gear, and I've got this little gear, right? This big gear's got some radius, we'll call it capital R. This little one has some radius, we'll call it lowercase r, right? And these two gears are touching. So in the system, right, I've drawn them separated, but in the system, they're touching, right? And if we say that the small gear is the drive gear, right, this is going to be moving, we'll apply some torque here, right? We're going to apply some torque on this lower gear. And I'll draw that torque again, but we'll call it, we'll put it in blue, right? So it looks different. So there's my torque, okay? So this idea of gear ratio is that why do we use gears, right? Why do we use gears? We use gears to transmit power, right? We use gears to transmit forces and torques, right? So we want to take a small amount of torque and increase it, or we want to take a large amount of torque and decrease it, right? We want to transform the amount of torque that is being produced somewhere, right? So if I have these two things, right, and if I'm drawing the free body diagram for them, and this is going this way, so it doesn't matter which way I draw this, right? But where these are in contact, there's some contact force that I'll call F sub C, right? And this is just the contact between the two gears, okay? But also at that point, right, because the two gears are touching, they both also have to have the same tangential velocity at that point, right? Because if they didn't, that would be weird, right? They're in contact and they're moving. So at that moment, they both have the same tangential velocity. That's going to be key in a second, right? So if this is going this way, then this gear, right? So to draw the motion, right, this is going to be my theta and my omega. We'll call this, right, and then this changes the direction, right? Because as this one rotates this way, it'll push here, and this one will rotate the other way, right? So with gears, where they interface, the driving gear is going to rotate in one direction, and then the other gear will be forced to rotate the other way, right? Like that. Okay. Great. So if we can figure out what this force is, right, then we should be able to figure out what the output torque is, right? But before we even talk about that, we can talk about gear ratio, right? And it comes from this idea that because the tangential velocity, V sub tangential, we'll call it sub L for the large gear. Well, you know, we don't need to do that. We'll just call it the same thing. Right? This tangential velocity is equal and opposite here, right? Because this one's rotating, no, they're both going this way, right? This one's rotating this way, and that's going to cause this, right? So I have the same tangential velocity on each of those points, right? But I want to find omega, right? Well, omega times r is equal to tangential velocity, right? Yeah? Please say yes, because it's true, and we learned about it a few weeks ago, right? So yes. Yes, all right, so omega times r is v sub t, right? Okay. So omega is just v sub t divided by r, right? But this v sub t, these two v sub t's are equal, right? So let's write it this way. For the small gear, v sub t is equal to omega times little r, but for the large gear, v sub t is equal to omega times big R. But those two things are equal, right? And so I'll call this one 1 and this one too, just so we have them numbered, right? Okay, so if I set these equal, I get omega 1 times big R is equal to omega 2 times little r, right? And essentially, I've come up with the gear ratio at this point, right? Because I can say, well, omega 1 over omega 2 is equal to little r over big R, right? I can isolate both of those variables. Now, either of these is known as the gear ratio, right? So what is this idea of the gear ratio? Well, the gear ratio allows us to know how much our torque changes, right? Because what happens is that my input torque, T, multiplied by the gear ratio gives me the output torque from my other, right, from my other gear. So what does this tell us, right? This tells us that if the gear ratio is the small gear divided by the large gear, right? Small gear divided by large gear, the bigger that this R is, the smaller my gear ratio is, right? Which means the less torque I produce on the back end. So this is a torque reducing system, right? It's a torque reducing system. It's also a speed reducing system, right? Remember, power is torque times angular velocity, right? And this is a little bit off topic for this class in particular, right? We're not going to go super in depth in a lot of this stuff. This is more of stuff that you guys will hopefully talk about with Professor Higgins when you go through like mechanisms and all those things. Right, but there's this idea of gear ratio, right, that we kind of brought up last class that people are a little bit confused about. I don't know if this is helpful, if this made it clearer or more confusing, but the idea here is that if we know how much torque we have in and we know the gear ratio, right, then we know how much torque we have coming out on the other side. We can do the same thing for the speed, right? If I wanted to solve here for the speed, omega 1 would just equal the small gear radius over the large gear radius, or the gear ratio times the output, or the omega 2, right? Which is what we used in our problem. We'll go back over that problem again in a few minutes. All right, hopefully that helped clear up gear ratio a little bit. Was there anything else that you guys wanted to talk about? No, nothing really. Okay. Well, there's nothing else. You guys got a homework due, not this weekend, but next, right? So Sunday after Thanksgiving, homework and learn some art. And the CLC stuff, due at the end of the semester. We'll talk about that right after this slide. So we'll go through everything in depth and what it all means. What I would like is by Sunday, if you guys could split yourselves into groups of 3, right? Because there's 9 students in the class. So if you could put yourselves into groups of 3, that'd be great. And one person from each group send me a private message or an email letting me know who your group is so I can set it up. All right, please do that by Sunday. That would be really helpful. Because the sooner you guys get started on these is going to be the better, right? So there's 3 parts left to this assignment, right? There's first the VOT build-in test. So what is this, right? So you got to come up with your design in your group. Right, in this assignment, you're going to construct your vertical axis wind turbine using the specifications from the design document that's in LoudCloud. Okay. There's certain specifications that you have to meet. One of those things is, so in the past, some groups have built full-size wind turbines. We're not going to do that. You guys are going to build desktop models that we can test inside of the wind tunnel. I have to talk to Dr. Williams and see if the wind tunnel is up and running. If it's not, we have a compressed air pump that we'll use. Um, it's not super, it's not ideal, right? It's way cooler if we do it in the wind tunnel, but it gets the job done, right? So you're going to submit, we'll talk about how to do this when we come back next week on Wednesday, right? But you're going to submit to the lab staff STL files for 3D printing. Right? We're going to 3D print our turbines. They have to fit on a specific shaft, which I have some, but I should have got before, so I'll grab them right now. At least the last time I saw them, we'll find out. Excellent. So each group one of these. And the wind turbine has to use this as a central step. Okay? I'll hand these out next week on Wednesday, which you can have them if the group wants to come and use the product. Right? But we've got one. If you print it and you find out that, you know what, this doesn't fit, it doesn't work, or want to print a different design instead, you can do that. But every redesign costs you a 2-point deduction every time you want to do it. And to be honest with you, it's the end of the semester, and I don't know what the lead time for the 3D printer is going to be because there are other classes that are going to be trying to use it. So typically when you design for things that have holes, you want to undersize them in 3D printing because you can always ream it out, right? But you can't ever put the stuff back in. So undersized is probably a little bit better than oversized just because if you did mess up, you're at least giving yourself a fudge factor in the right direction, right? You want to be sure that the VAUGT addresses the following criteria. One, that the turbine is inexpensive in terms of components and manufacturing. Okay, so the way this assignment was originally written, you guys were going to be making these things from like buckets and pieces of wood, right? Things that you would find lying around in an underdeveloped country. But it's not the case anymore, right? What you're testing is you're testing the form factor. So when you write the paper, I want you to write it as if you're talking about the full-size machine that you're going to build, right? But when we're testing it, it's going to just be surrogate parts made of 3D printed materials, right? Does that make sense? So when you're writing about it, talk about the actual full-size machine that you're building and what the parts are going to be. And it has to be inexpensive, right? What's inexpensive mean? Well, look on the market and do a little research and see what other vertical axis wind turbines sell for, and you want to be right in the pack, right? You want to be a little bit under what they sell for. The design is to use component, right? So that's your overall design. The vault should be a maximum height of 6 feet. So these are all, right. I'm gonna have to give you guys another document. I'll post it to LoudCloud by Monday with the design specifications for building this as a test tabletop model, okay? But these are good things to know because your real life system has to be maximum of 6 feet tall and 3 feet wide. The turbine has to be able to produce the minimum power required to operate your system. Okay, so when we do our test, we have little boxes that these shafts go into, right? We have a nice coupler for them, and that's connected to a generator, and we can see how many volts you're producing, right? Then you can determine how much power that is. The way that we're going to, the way that you're gonna kind of go about this is you're gonna assume that if your tabletop model is like 10 times smaller than your real life one, that you require to produce 10 times less power, right? We're gonna assume that it scales linearly. The vault is freestanding, right? So if it falls down while you're testing, that's no good. If it breaks while you're testing, also no good, right? We're going to refer to, yeah, there's a checklist for this for the grading, okay? So that's the build and test. Essentially, what you're going to do is you're going to meet with your groups, decide on the design, mock it up in SolidWorks, scale it down to be the appropriate size to be going in the wind tunnel, send the files to be 3D printed to, I think it's lopeslab@gcu.edu. I forget the actual email address, but I'll get you guys all that by Monday, okay? The sooner we start this, the better, because if you can get your 3D prints in early, that gives you a little time to change it if you want to, right? First design change is free, by the way. You get one free design change. Everything after that comes with point deductions. What about the paper, right? So there's a design paper that's associated with this. So the things that you're turning in, right? The build and test is important because you're going to get data from it. And also it's going to prove your concept, right? But then you take that information that you learn and you have to make a paper. And I've pulled all this just from LoudCloud. This is just from the assignment description in LoudCloud, right? So this is a CLC assignment, right? So one paper per team, right? You work with your partners, right? Your vault design should include a simulation in SolidWorks. So you want to do some airflow simulations, right? For on campus as well as on location. You need detailed drawings as if you were going to give this to a machine shop to make it. You need to estimate your power output. Power equals torque times omega. Yeah. This is Newton meter. What is it? It's Newton meter radian per second, but a Newton is a kilogram meter per second squared. It all washes out. It's interesting. So detailed drawing, power output estimates. Your vault, right? This is your vault has to be a maximum of 6 feet tall and 3 feet wide. It has to be freestanding, right? So if you apply your simulation and it falls down, material list, right? So basically, you need to provide a bill of materials, right? What are you making this out of? Are you using, PVC pipe? Are you using Home Depot paint buckets, right? Like what specifically are you using? How much does it cost? How many of them do you need? You need detailed, a complete drawing package must be turned in prior to your presentation. All right. I have this and the presentation on the same day. I don't need it right before your presentation, right? I don't need you to come in and like hand me this paper, right? Turn it in. They're both due on the same day. It's the last day of the semester, okay? Due on the 18th. Not required to submit this assignment to Loops, right? It says. So it's fine. Remember, it's a CLC, so one submission per team is fine. It'll automatically link all you guys. Okay. So that's, any questions? Yeah.
The paper is a CLC too?
Yeah.
Okay, so we all need to write the paper together.
Yeah. The paper, the presentation, and the build and test are all CLC assignments, so they'll be graded as group projects. Talking about the presentation, you guys have to do a 5 to 10 minute presentation. This will be the last day of class, right? We'll all come in, we'll do our presentations, right? The way that I run them, you stay for all of them. There's only going to be 3 in this class, so that's not really that big of a deal. But for larger classes, sometimes people think I'll just do my presentation, then I'll leave, and that's rude because everybody else watched yours, right? So we're not going to do that. So you do your presentation, right? The first half should describe the problem that you're trying to solve, right? Why did you pick to deploy your vault, where you decided to put it, right? You need to discuss how the design of the project relates to the Christian worldview. And in the second half, do a detailed description of your design, right? Talk about your simulations, talk about your build-in tests and results, include blade details and power outputs, as well as cost analysis and components selected. You're going to submit your PowerPoint presentation to LabCloud. It says annotate each slide with your presentation notes, but I'm going to watch your presentations in person, so you don't have to annotate them. Like, just if you don't want to. I'm not really looking for that, honestly. Yeah, APA, whatever. Solid academic writing is expected, so make sure that you're citing things. It uses a rubric, so make sure you do the rubric. After your presentation is done, there's obviously a questions period, right? So anybody from class or myself can ask questions. I might try to invite some other faculty just to round it out for funsies, right? So they, but outside of that, I think it's a pretty standard presentation, right? So you write the paper and you do the build and test, and then you basically present on your paper, right? And your results. That's about it. Everybody in your group is required to participate in the presentation, right? So like you have to do a little bit of the presenting to get points. Okay. You guys have any questions? Yeah, Logan.
What type of annotations do you want for slides? Because it says annotate each slide with your presentation.
Annotates each slide with your presentation notes. I mean, I'm going to be 100% honest with you. I am not going to look at the presentation notes. I'm not. It's that is like trying to force you, in my opinion, that is trying to force you into a presentation style that you may like or you may not like. And if you want to put notes in the slide notes, go ahead. That's fine. If you don't, that's also okay. In terms of like citations and things, if you take a picture from a website, make sure you cite it on the slide, right? Like underneath it. That's just common. That's the common thing, right? But I'm not going to look for your notes, your personal notes or anything. I don't find it. I find it more useful to watch your presentations and pay attention to what you guys are saying and how you're saying it. And whether or not, and okay, here's the other thing. Just because you didn't answer something directly in your presentation, like if you get a question about it, that counts as presentation time too. So if you can show knowledge of something by answering the question about it, right? And so just keep that in mind too. You don't necessarily have to have everything on there. If you feel like you're getting a lot of questions, that's okay, right? Because fielding questions is a big part of doing presentations. It really is. Okay. Anything else?
Is this like a presentation or?
Yeah, it's a group.
What if the printer fails itself?
The 3D printer?
Yes.
Man. Well, we'll have to burn that bridge when we get there, Brandon. I mean, yeah, if for some reason we can't get prints done, then we're gonna have to default to how we had to end the semester for ESG 360 last year, which was you just do the paper and you don't have any results section. Right, so all the rest of the points get collapsed into the rest of the paper. Yeah, I mean you can do that too. Get a laser pointer and I'm just imagining you guys sitting around like trying to melt sheets of ABS and yeah. Anyway, yeah, we'll figure it out. If something weird, we have run this project in catastrophic conditions before. We can figure something out. If for some reason, so the printer failing and you failing to get your prints to the lab staff on time are two different problems though, right? So make sure you come up with I honestly, it's the end of week 11. I would shoot to get them in by beginning of week 13 if you can. And I know Thanksgiving is happening next week, right? And I get it. But we're almost done with the semester, right? One big push left. This is the biggest assignment for the whole class, right? These three things make up a majority of the points that we have left. Really focus on punching this one out, right? Get a big push. The last week of class, we won't do any content stuff. We'll just be trying to do build and test, and that's you know, just trying to get things straight. Okay, I'll post some other supplementary material for this by Monday, probably this afternoon when I get back to my office, because I have a bunch of stuff on my computer. And if you have any questions, right, let me know. Yeah, Logan.
So for 5 to 10 minutes, so that's including questions from like the audience or just you?
So the 5 to 10 minutes is just the you talking time. There's only 3 groups, so class that day is probably gonna be pretty short. We'll probably be done in less than an hour. I normally, so based on previous experience, I normally don't ask that many questions, right? So I will definitely at least ask one question of every group though. Like feel like I'm not doing my job if I don't ask you at least one question. Now I have been at conferences before where I've seen some really fantastic science offs, and then none of that's going to happen, right? I'm not looking to attack any of your results or anything like that, okay? But know that in a non-controlled environment, some people just want to watch the world burn, right? That's how it is. Okay. So, in honesty, the whole thing will probably take about 15 minutes with questions, right? Okay. So we're looking at probably like the last day of class, you guys get out of here with like 2 hours of your life to desperately try to find an Xbox or PS5 online, but that's not going to happen until at least March. So. All right. We good? Any other questions? I'm sure more things will arise as you guys start working on it, right? Remember, office hours today from 3 to 5, Monday, 9 to 11 a.m. Tuesday, Wednesday, next week from 3 to 5. We still do have, that's a good announcement to make. We still do have class on Wednesday next week, right? It's not canceled. The university has sent down the edict that, they don't really want students traveling for Thanksgiving. You're all adults and you can do what you want, right? I'm not going to tell you to do one thing one way or the other, but to tell you this, that the university policy is that they don't want you to be traveling, and we still have class in person after Thanksgiving, right? So any rumors that you may have heard that we're going to be moving back to online for the last few weeks of the semester is not true. We're going to be in person the rest of it till the very end, right?
Do you know what next semester is going to look like?
As of right now, from what I know, next semester is going to look a lot like this semester. If it's still going to be, it's going to be dependent on class size. So most of you guys will probably be taking ETG 410 next semester. And that one's going to be just an in-person. We're moving it to a classroom that's big enough to let us meet in person. I think last time I heard. Other class, so for the MET and EET classes, right? That's probably, it's going to be probably like what you guys are experiencing, probably business as usual. For the rest of the university, right, it's still like, if you're not taking the MET and EET classes, you might have blended, you might have broadcast, you might have whatever the new hotness of Zoom learning is, right? Okay. So this is where we left off last class, right? We did the first part of this, right? But just to recap, what did we were talking about work and energy, right? We're talking about work and energy and for rigid bodies. And turns out that because work and energy are scalars, we can just add it up, right? We can add up rotational and translational because it's about the total amount of energy, right? And then we walk through that problem before this where we had the pulley with the mass. Right. So what about this one, right? So to refresh, right, I've got a system that's at rest when a moment of m is equal to 6 Newton meters is applied to the gear B. If I neglect friction, I want to determine the number of revolutions of gear B before the angular velocity reaches 600 RPM. And I want the tangential force exerted by gear A on gear B. Okay. So first thing we have to do, right, is we have to draw our state diagrams, right? And I wrote up there that state one is at rest, and therefore the diagram is not interesting because it would just be two circles with no arrows or anything. So I didn't draw it, right? Well, that's fine, because at least I said that it's at rest, right? And state two, well, I've got some moment that's been applied to gear B, which gives me some angular velocity, omega of B, which will also generate some omega A, right? And I said, well, I can write my knowns here, right? I know MA, MB, KA, KB, and RA and RB were given, right? And remembering that KA, remembering all the way digging deep, really deep back to statics, right? We remember hearing about the radius of gyration, but never ever using it in statics. Well, here it is, right? What is the radius of gyration? Well, the radius of gyration is if we imagine that all of the mass of an object is centralized at one point away from the axis of rotation, that's the distance it would be. Okay, and why is that useful? Well, it's useful because it allows us to calculate our mass moments of inertia. So if you're given K, right, you square it and multiply it by the mass, you get I. Okay, and that's why it's useful. Right, we also had to convert omega B from 600 RPM into radians per second. Right, so I wrote down my equation. I know this is a work energy problem because I was asked for displacements, right, and forces. So the kinetic energy of state one plus the work that it takes to go from state one to state two is equal to the kinetic energy at state two. Well, I know at state one it's zero, right? Because everything's at rest. I also know there's no potential. Well, we're not even going to talk about potential energy here, right? We're not. So what's the kinetic energy at state two? Well, that's 1/2 I omega squared A plus 1/2 I B omega B squared, right? Right, so it's the rotational kinetic energy of both of these gears. There's no translational kinetic energy, right? We went over that. Why is there no translational kinetic energy? Well, they're gears, they're fixed. They're just going to spin in place, right? Hopefully they're not translating. That would be pretty bad. Great. We've got all this set up, right? We move on. And this is where our gear ratio comes in, right? We talked about this a little bit at the beginning of class, right? If you have a tangential velocity at the center point, you get omega A times RA is equal to RB times omega B. I want to solve for omega A because I know omega B. And when omega B is 62.83 radians per second, and we multiply by our gear ratio, we find out that the larger gear is moving slow. Awesome. So we can calculate T2. Right, 1/2 times 0.4 times 25.13 squared plus 1/2 0.0912, right? So kinetic energy of A plus the kinetic energy of B, and I'll get 164.2 joules. So now I have to determine my work, the work that it takes to go from state one to state two. Well, the only thing that I have on here, the only force, the only moment is that moment that I applied. And that's going to move theta 2 from position 1 to position 2. But if we consider position 1 to be 0, because we just want the difference, right? We just need to know how far it's moved. Well, then we can say that this is equal to 6 times theta 2b, and we can solve the whole thing for theta 2b. which is 27.4 radians or 4.36 revolutions, right? We went through all this last class. You can always go back on YouTube and watch how we got there, right? But hopefully you've got it in your notes, and that was just a quick recap. Because now we're going to do part B. And part B is to find that contact force, right? Remember, I was talking about earlier when we talked about gear ratio. What is the contact force, right? That tangential force. So for part B, the first thing I need is a free body diagram, right? This is going to be of gear A. And gear A has omega A. And if I remove it from the other gear, it's also got some tangential force that I'll call F sub T in this case. I called it F sub C for contact force on the previous slide, or at the beginning of class, but it doesn't matter what we call it, right? There's some contact force, we're calling it F sub T. So if I want to find this force, how am I supposed to do it, right? Well, we can use the principle of work and energy to do it. Okay, so how are we supposed to do that? Well, I need to figure out how much work that initial moment did on this gear. That seems like a weird thing. Is it really that initial moment? No, if I'm looking here, right, this force is going to produce a moment, right? It's going to cause this to rotate in some way. It's not going to translate because we know it's pure rotation. So it's going to cause this to rotate. Okay. Right. Let's draw a coordinate system. So this will cause it to rotate in some way. So this force is going to produce some rotational work, right? Because as I push it on the bottom, it's going to cause a rotation, right? And so I need to know what that moment is, and I need to know how much angle this goes to. Well, how am I supposed to figure out the angle that this moves through, right? So let's write down our equation, right? T1 plus U from 1 to 2 is equal to T2. Well, remember, that's still 0. In this case, if we've isolated half of the system, right, T2 is just IA omega A squared, right? I've taken away half of the system. I'm only analyzing the energy of this portion, the working energy on this portion. Turns out if you crunch the numbers here, this is 126 joules. What about U? From 1 to 2. Well, this, since it's rotating, we'll call this 2A minus 1A, right? But we're going to do the same thing as before. We're going to say that at start, this is going to be 0, right? This is not moving at the start. It's at 0, right? But I don't have a moment. But what I do have is this applied force, right? And this applied force is a certain distance away from the axis of rotation, right? So I can create the moment as seen by that force. It's just going to be F times R sub A times theta 2A. All right. So how do I find that translation? Or I'm sorry, that rotation angle? How do I find that angle? That's the question, right? That's the key. Because once I find that out, I just have to solve this equation for F. So how can we talk about that? Well, all right. Let me frame it this way, right? We talked about this before, right? Right. We know that How do we know that? Because the tangential velocity of each of the center point has to be the same. It has to be the same. Okay. Well, isn't this just this? Right? That's the time derivative, right? So if I take the integral of velocity, I should get position. So let's do that, right? So I'll end up with theta A, well, RA is a constant, and RB is a constant, right? But there's some, right? If we're going to do this for real, right, there's some constant associated with this. So we can, but remember, our initial conditions are 0, right? So that's just going to end up going away because that's going to tell us that, you know, theta of A is 0 and theta of B is 0 initially. And so those terms cancel and we're good. Look, we've got this. Well, theta A is therefore equal to RB over RA plus theta B. We can use the gear ratio again. We can use the gear ratio. .1 over 0.25. We found theta 2 in the last part of the problem, right? That was 10.96. Theta 2b, right, in the last part of the problem, which was 27.4 radians. It turns out this theta A is 10.96 radians. So you can put that into our equation, right? We've got F sub t times RA is theta 2A is equal to 1/2 IA omega A squared. I can plug in these things, right? $126. If I solve for F, I get 45.91 newtons.
Why did you go to 1/2 inertia angular velocity?
Because that is the rotational kinetic energy, right? Because remember what we started with, Nathan, right? We started with our work energy equation, right? And so this is 0 since we started at rest. So we have the amount of work that we did has to be equal to my final kinetic energy.
Okay. So it's just kinetic energy for rotation?
Yeah.
Okay.
Remember, when we talk about I, like the rotational mass moment of inertia, that is the equivalent to mass in the translating systems, right? They're analogous. You guys have any questions on this? All right. Nothing? Okay. So, it says scan it and send it to me as loud code before leaving class today. We're not going to do that. We're just going to do it and talk about it, right? So I want you guys to take, say, 20 minutes and start working on this. I'll come around and talk about it, right? So what is this? I've got a force P of magnitude 3.8 newtons that's applied to a tape wrapped around a body indicate, right? So imagine this is a roll of tape, okay? And it's sitting on it's sitting on this horizontal surface, right? And you're kind of applying a force to the end, and you're like kind of trying to pull this errant piece of tape off, right? So you're like, I'm just gonna pull here, right? With a constant force of 3.8 newtons. I'm gonna assume that the mass of a thin hoop to be 2.4 kilograms. I want to determine the acceleration of point A and the acceleration of point B. So here's point A in case it's not clear. There's point B. So I want the acceleration of those points. In case you guys wanted to know, I for a thin hoop is equal to mass times radius squared.
So the tape like attached to it, or
So what's, sorry, say that one more time. Zach.
the tape isn't like in the motion of it kind of slide off.
So imagine that there is some, imagine this is like a solid piece of plastic, not like a tape measure tape, not like Scotch tape. So it's sitting in a hoop, and you're gonna pull on this one part right here. No, we're just gonna talk about it since you guys are all here. We're good. Few more minutes. All right, guys. You're fine. That's 20 minutes. The time flies when we're having fun. I know. All right, so what kind of problem is this? What should we pull out of our toolbox? What's that? Everything. Well, what are we being asked for? We're asked for accelerations, right? Think back to class on Wednesday. I know, big ask. All right, think back to class on Wednesday. I had that flow chart that was up here, right? And I had the three categories of problems. You got impulse and momentum, where if you're asked for velocity or time, right, that's when you should be looking for impulse momentum. If you're asked for forces, distances, or velocities, that's work and energy. And when you're asked for forces and accelerations, that's Newton's law. Right. So which one of these does that fall into? It's Newton's law, right? So we should be able to use Newton's law here. That it's a throwback, right? Because it's not, well, I'd say throwback loosely, right? Because it's not the work energy stuff that we've been working on. So it's a Newton's law. So we need to find these accelerations at point A and point B. Okay? And so if I pull this, right, this is gonna, because it's taped, right, this will extend a little bit, but it'll also, as this part rolls, right, as we unroll it, it will also slide, right? It will also slide on that frictionless surface. I'm gonna pull this, right, it's gonna unroll a little bit, but it's also, so there's gonna be some rotational thing going on there, and there's also gonna be some angular, or some translational velocity. So we've got both. So we got to start with the free body diagram since this is Newton's law problem, right? And the free body diagram is not that bad. We'll do our FBD and our KD. So here's my FBD and KD at the top. All right, so it looks just like what you thought. Right here it's sideways, you can draw it up and down. You can draw it however you like, right? The important thing is that we've got P going one way, right? And this is going to cause the center of gravity of the thin hoop to move, right? As it rotates, okay? Because remember, with rigid bodies, if I know the velocity of one point on that rigid body, I can find the velocity of all other points. Okay?
One of the main things that you use with P, why is the radius the same? Like it's like being pulled down, right? So like
Good question, right? So we're talking about the instantaneous acceleration, not the continuous one. So at this, imagine this as at this moment of time, you were able to take a snapshot and you have all the data associated with just this point in time, right? And so that's what the radius is then, right? You're right. If you continue to pull this, right, this will continue to unravel and other stuff will happen, right? And the radius will likely, well, I mean, depending on how you want to think of it. If it's the radius to the outside, right, it'll get a little bit smaller every time, right, by the thickness of the tape. But if we're looking at this for the instantaneous acceleration, when everything is in this exact configuration with R being this R, then that's what we're looking at. Okay. So we can do our Newton's law stuff, right? We'll sum the forces in the x direction. We sum the forces in the x direction. I can find an acceleration for the center of gravity, a sub x, and that's going to be my force divided by my mass, which are two quantities that I know, right? And our problem was 3.8 and 2.4. I can sum the moment about the center of gravity, which tells me that I alpha is equal to P times R. And I can solve for alpha, right? So now I have a equation for alpha in terms of P and an R, and an equation for acceleration in terms of P and M. So it's looking good. And now I'm here. Yes, I can write the acceleration of point A is equal to the acceleration of the center of gravity plus my tangential acceleration minus my normal acceleration. And I can do that for both of these points, right? So this is where we're going to hit. And it turns out that omega at this moment in time is actually 0. Actually 0. How are we supposed to know that? Indeed, how are we supposed to know that? Is it stated in the problem statement? It says the body rests on a frictionless horizontal surface, right? So we're going to assume that since it rests, that the initial speed is 0. Well, how can you have an acceleration if the initial speed is 0? Remember, this is instantaneously, at this moment. At this moment in time, maybe it was moving the other way, and we started applying acceleration in the opposite direction, and so we've just switched the direction of our angular velocity, right? That's how we come up with that. Okay. So we take those equations, right? So I'm going to start with AA. Well, alpha A sub x was P over M. We found that. I can take the cross product of alpha cross R, right? Alpha is in the K direction. So we've got P over M times R. J is negative R, right? Because to go from the center, if I go from center of gravity down to A, it was negative R on my drawing in the J direction. So, yeah, go there.
Sorry, I was just looking at that. Should that equal 3.6?
Good. Let's see. Could be. I could have fat fingered it. Stranger things have happened. 2 times 3.8 divided by 5.4. I got 1.41. 2.4. Why did I put 5.4? That is strange. Please hold. My bad. Yeah, 5.4. Oops. It's Friday, guys. Yeah, Friday brain. Good catch. Good catch. Yeah, my bad. So what happens here, right? If we take the cross product here, we'll get P divided by MR times R, which leaves me with P over M. So it turns out that the radius actually just doesn't matter for the thin hoop, right? Doesn't matter. It's going to go away. So we can always find the acceleration like this. We'll get 5.4 meters per second squared at A. We can do the same thing for B, right? But R is just going to be flipped, right? Instead of being negative R, it'll be positive R. And because this is positive, this is going to make this negative, which means that I have no tangential acceleration at B. Massive itchy, man. Come on, GCU. There's also these GCU masks, these ones. Okay, you guys remember in high school we had to wear the double layer gym shirt so you could switch teams if you needed to, right? One side, my high school colors were red and yellow. So one side was red, one side was yellow. It was the grossest shirt ever. Super hot. It was like this mess. It was like a double, wearing two t-shirts at once. It was ridiculous. But anyway, that's how I feel wearing this mask. And I know that you all feel much better knowing that now. I know that. Okay. All right. So we'll do a couple problems and we'll see. Maybe we'll get into impulse momentum today. If not, we'll get into it on Wednesday. All right, we'll see what happens. You guys have any questions on that last one, that Newton's law problem? No?
What was the last slide?
This one?
What is the
3.8 is given in the problem statement. It's the value of the force. It's P.
So the AX that you solve for by the force by the mass,
Mm-hmm.
that's the tangential acceleration, or that's the acceleration pointing towards the center of the circle?
That's the acceleration of the center of gravity of the hoop.
So,
Right, so-
when you do, so that equals MA, like it's always R is the center of gravity.
Yes.
Okay.
Because remember, for rigid bodies, what we really want to talk about, right, is we want to talk about how is the center of gravity of this object moving, right? Because this rigid body is just a collection of particles, right? And if we know how the center is moving, then we can talk about how everything else is moving.
Okay, so it's just like a translational about the center of gravity.
Yes.
Okay.
So the answer for the acceleration is 0.
Yes. So it's moving at a constant velocity at the top, right? Which I think, if we think about it, right, what's happening, right, with this? The bottom, that tape is getting longer as we pull it, right? That's going to cause an acceleration as we move, but the top is going to be moving at the same speed, right? So the entire body moves with the speed, but the bottom is moving faster because there is the extension of that tape. Well, that point is accelerating. There's acceleration to that point. Almost like a weird, it's like a weird no-slip condition, right? It's like a strange no-slip condition. Right. Okay, good questions. Problems. Oh, this is a good one, right? So I've got a 30-pound slender rod, which pivots about 0.0, right there. The other end is pressed against a spring that has a spring constant of 1,800 pound per inch. I compress it 1 inch, and the rod is in the horizontal position, right? So in this initial go, right, I'm already pushed, this is already 1 inch compressed, right? So there's some amount of energy stored in that spring already. If the rod is released from this position, we need to find the angular velocity and the reactions of the pivot as the rod passes through the vertical position. So state 2 is going to have this straight up and down at point O. Okay. So what kind of problem is this? We're asked to find angular velocity, right, and the force. So what are we working at? Velocity and a force. What's in our toolbox right now for rigid bodies? We've got Newton's law and we've got work energy. Which one of those two fits this problem? Mm-hmm. Right, let's do show of hands. Who thinks is Newton's law? Who thinks it's work energy? It is. It's work energy. It's work energy, right? Because we're asked to find a velocity. Because we're asked to find a velocity and a force, right? And even better than that, we can actually use conservation vector on this. Right? Because we're going to ignore any friction, any losses. We're going to assume that this is a conservative system because we weren't explicitly told that it wasn't. Okay? So the first thing we have to do is draw our state diagram here, right? So let's do that. My state diagram has got this thing, right? We're going to say this is point O over here. That's O. Point O has some reaction forces associated with it in the X and the Y direction. I've got the center of gravity over here, which I conveniently drew over with my O. But we'll say the center of gravity is here. Right? That's OX right there. I know that this distance is 1 foot, right? So that pivot point is 1 foot from the end. At its initial state, there's going to be some velocity upward, right? Well, we're told that it starts at rest, so that's 0. So why would you even draw it, Dr. D? Good question. Why indeed? To remember that that's got to move up in the up direction, right? Because there's another thing that we need to talk about in a second. What about this? We've got 5 feet here. This is 2.5 feet, right? We were told that the whole thing's 5 feet. The centroid for a bar is just halfway across the bar. And we also have this, which omega 1 is equal to 0. And I'm going to set my datum to be even with my point O, right? The pass through point O. So this is state 1. This is my initial state. I have this spring compressed right now. I haven't shown it, right? But I'll put it right here so we don't forget. There's some spring force pushing back up, right? There's some spring force fighting me. When we get to point 2, to state 2, point O is still on this line. But now we are in the completely vertical position, right? And we'll have some omega 2, our center of gravity. We'll have some V2. Of OX and OY. This distance, right, is still 1 foot. The entire bar itself is still 5 feet. And so that means that this distance has to be 1.5 feet, right? Because it has to be the rest of the distance to recreate that 2.5 feet, because the center of gravity will still be at the same distance. State 2. We want to find omega 2, OX, and OY. Those are the things we need. Things that we know. The weight of the bar, 30 pounds. Our initial displacement, I'm going to call it delta X, is 1 inch. And my spring force is 1,800 pounds per inch. Questions so far? Everybody, we tracking? Just as a spoiler alert, you guys are gonna have to do the next one. I'm tired, I'm old, my bones hurt. Okay. No, nothing, we good? All right. So what do? We can start our equations here, right? So let's talk about state 1. Seems like a good spot to begin, right? At state 1, what do I have? Remember, I'm going to use work and energy, right? And work energy tells me that T1, well, specifically conservation of energy, plus V1, I don't know why I drew it like that, just V, just regular old V, is equal to T, well, my overall equation, right? Conservation of energy tells me T1 plus V1 is equal to T2 plus V2, right? And that's the total kinetic energy at state 1 plus the total potential energy at state 1 is equal to the total kinetic energy at state 2 plus the total potential energy at state 2, right? When I say total kinetic energy, I mean any of the rotational and translational kinetic energy, right? When I say total potential energy, that means all of the gravitational and elastic, right? So anything due to being higher or lower than the datum, and anything due to being connected to a spring, right? So at state 1, do we have any kinetic energy? Sorry, as I said one more time. So the 1/2 m squared, that was your mv squared? That's the formula for kinetic energy. Do we have any kinetic energy? Yeah, but in state 1, what do we have? Do we have any? Yeah, it's all potential to start with, right? Because in state 1, everything's 0. So T1 is 0. What about my potential? What do I have as potential energy in state 1? Just state 1. Well, have I shifted off of my datum at all? Remember, this is my datum right here. I shifted off of my datum. Remember, potential energy due to gravity is measured from some point, which is arbitrary and which we can pick, right? What are we measuring? We're measuring the distance of the center of gravity to the datum. Center of gravity is in line with our datum, so there's no gravitational potential, right? Because it's at the line that we're starting our measuring from. Datum is a fancy way of saying this is my 0 line. I'm measuring everything from there. If you're there, then you're 0. What about spring? Do I have a spring in this problem? Yeah. So what's my elastic potential energy? Who remembers how to find elastic potential energy? There it is. 1/2 kx squared. We know k. It's not really x though, right? It's delta x. It's how much have I compressed that spring, which we have. So we know all this. This is 1/2 times 1800 times 1 squared. All right, so this is 900 inch-pounds, which if we went through and did the conversion, right, this would be 75 foot-pounds. Okay? Great, so we have that. So we know now what the left-hand side of this equation is, right? We have the state 1 part. Now we just need to figure out state 2. We need to figure out state 2. So it's state 2. Let's talk about potential energy. What kind of potential energy do I have here? Would I expect to have any elastic potential energy here?
No.
No, right? Because the spring is not compressed anymore. So delta x is now 0. What about gravitational potential energy?
I mean, it could fall, but, you know.
So remember, that's measured for, well, all right, so what's the formula for gravitational potential energy? Who remembers?
Force of gravity.
Say that one more time.
Mass times gravity times the change in height.
Yes, MGH has the center of gravity of this object changed its height with respect to the datum from state 1 to state 2. Yeah, right? So there is gravitational potential energy now. We've converted some of our energy into gravitational potential, which is mgh. And in this case, that's going to be 30 because m times g is just the weight, which we already have, times 1.5. We write that so people can actually read it. 1.5. So this is 45 foot-pounds of potential energy at state 2. What about kinetic energy? What do I have? I've got both flavors here. I've got translational and I've got rotational. I have both flavors of kinetic energy, right? So I've got 1/2 m v2 squared plus 1/2 I. Sorry, I'll get there. 1/2 I omega 2 squared. But we kind of run into a problem because I don't know v2, but I also don't know omega 2, right? But I'm only looking for omega 2. So can't I just say that 1/2 m, can't I say that v2 squared is just omega 2 times r squared, right? Because v2, the velocity of the center of gravity, is just the angular velocity times the radius, right? Times the distance I am away from the center. What's I for a beam, right? Well, that's 1/12 times m L squared. Where did that come from? Again, that comes from the table. We see a beam a lot in this class, right? It's one of the most common things, right? And I keep telling you guys that you guys will just end up remembering it at some point, right? We'll just end up remembering it. We can plug the rest of our numbers in here, right? We know m, we know r, we know L, right? L is just the total length of the beam. So let's do that. Let's plug all this stuff in my state 2 equations. Come on, PowerPoint. I know you can change slides. I've seen you do it before. I would like for you to change slides, please. Thank you. All right, so T2, if we plug in the rest of our numbers, right, we get 1/2 of 30 over 32.2 times omega 2 r squared plus 1/2 of 1/12 times 30 over 32.2 times 5 squared times omega 2 squared. Sorry, I should have put a 5. No, it's not a 5. That's, oh, weird. I don't want to put that in. This r here is 1.5, right? It's the distance from the axis of rotation to the center of gravity. This whole thing is also square. So it turns out if you run the numbers, we just get that 2.019 omega 2 squared. So we can take our conservation of energy equation. We'll set that equal to 0, and we'll plug in the things that we have. So I've got, and everything right now is in foot pounds, right? Because I have everything in foot pounds. And there we have it. We've got omega 2. All right, so how the heck are we supposed to find these forces now, right? These reaction forces. Oh.
Okay, so I guess that's the V1 is 0.
So what was that, Zach? Sorry.
No, that's right. V1 is 1 and 0.
No, T is the kinetic energy, V is the potential energy. So we have no kinetic energy to start, but we have potential energy due to the spring storing some energy. So we want to find the forces, OX and OY, as we pass through the second position. That's what we want. So how are we going to do that? This is going to be a throwback. Oh, don't do that. No, thank you. All right. How are we going to do that? Right? Well, let's draw a free body diagram, right? Because I want to find the reactions. So here we go. I got this free body diagram. Here's my center of gravity. There's some weight that's passing through there. Here's point O. I've got OY and OX. I know that this distance from here to here is 1.5 feet. This is going to equal my kinetic diagram, right? My kinetic diagram is going to have I'm going to do something here. You guys are going to be like, but Dr. D, why? Why you do this? Okay. Mass, why I do this indeed. Why do I pick normal and tangential coordinates? Why not x, y? This beam will rotate in a circle about this point, right? That's a fixed circular path. That's a fixed path, a path of a fixed radius, which means that it's a great candidate for normal and tangential coordinates, right? Because when we have a curvilinear path that has a fixed radius, That's when we want to use normal tangential. Okay, great. The other thing about it is, remember, you can say this, that the normal acceleration is equal to r times omega 2 squared, right? We've used that quite a bit. We also know that the tangential acceleration is r times alpha. So using this normal acceleration, right, I know r is 1.5, right? It's the distance to the center of gravity, times 3.85, which I just found, right, squared. So this is going to be 22.23 feet per second, right? Just in case we forgot, this is the KD, this is the FD. Okay. So I've got what? I've got how many unknowns? Well, I know a sub n, but I don't know a sub t, right? Because I don't know alpha. So I need to find alpha, I need to find oxy, or ox and oy, right? I've got three unknowns, and luckily, since we can leverage Newton's law now, I can get three equations. So what do you guys want to do first? Sum the forces or sum of the moments? What are you guys thinking? What are you guys feeling? Sum of the forces, which direction? Well, luckily for us, some of the forces in the tangential direction, right, is the same as x, and normal is basically the same as y. Please hold. And so let's sum the forces in the y direction. Sure. This is going to tell me that OY minus the weight, which is 30, is equal to the mass times the acceleration normal. That's sorry, and this is negative, right? Because it's pointed downward. Okay. So hey, look, this is negative 30 over 32.2. I know a sub n, which is 22.23. I just calculated it. So hey, look, right? This I can solve directly for O sub y. 9.29 pounds. One more thing we need to get, right? All right, we want to use our other sum of the force, or we want to sum the moment right now? Okay. Sum the forces in the x direction. I've got O sub x, and that's going to equal mass times the acceleration tangential, which is just mass times alpha times r, which I don't know, right? Because I don't know alpha. So I'm going to need the third one, right? So let's sum the moment. Where do we want to sum the moment? Let's ask the question. At what point on here, where should I sum my moment? The pin. Why would you want to use the pin? Excellent. It's more than that though, too. The weight passes through the pin as well in this configuration, right? So you have canceled out all of the forces. So the sum of the moment is equal to 0 if you use the pin. The pin is an excellent choice. Remember Dr. D's number one rule for selecting where you should shake your moment about? Always look for the place that has the most forces, right? Because you can cancel out a lot of your terms that way. So if we sum the moment at O, we have no forces, and that's going to be equal to what? Well, the mass times the acceleration, right? Look at our KD. The mass times the acceleration of n goes through point O, right? So there's no effective moment from this one. but there is an effective moment from here, and we have to deal with I alpha, right? So let's write the equation. If I sum my moments at O, I will get I times alpha plus M times R alpha times R. All I did was I substituted in R alpha for A sub T, right? That's all I did. And this is equal to 0, right? Because the sum of my moments is 0. There's no, if I take it at 0.0, I don't see any moments. Well, so you can do some algebra, right? And it turns out that both of these things have alpha in them, right? So this is just going to be I plus mr squared times alpha. Alpha is equal to 0. Cool. Take this, pop it back up in here, right? So O sub x is equal to 0. Because mass times alpha times R. Done. Nailed it. We're the best. We got 220. First of all, do we have any questions?
So like I know the math says LX is 0, but like, is it just because like anything that's just rotating, there's not going to be any?
So it's only at that position, right? Like once you move out of vertical, you're going to start accruing an X reaction force on that thing.
Probably has to on the other side.
I is the mass moment of inertia, right? And that's a lookup from the table, or you use k squared times mass to get it. In this case, we use the table, even though I didn't show you the table, but I use the table. A beam is a very common one that's 1/12 ml squared. If you need one for an exam, you'll be given it, right, or K, or you'll be given a table to look at, one of those options.
And like, so not going to inertia, it's just like, mass times velocity, but it's like,
So think of it as the mass moment of inertia, think of it as how much resistance you have to rotating something. So the larger it is, the harder it is to rotate something, right? It's essentially the equivalent concept of having mass in a translational system. Physically, what it is, it's telling us how is the mass distributed throughout our object, right? That's physically what it's telling us. But if you just think of it this way, right? The larger the number, the harder the time you're going to have getting it to start rotating. The smaller the number, the easier it is to have it start rotating, right? Okay. Any other questions? All right. I want you guys to spend the next, let me say the next 25 minutes work through this problem. Very similar to the last one we did. So I've got a slender rod that's 4 kilograms, and it can rotate in the vertical plane about a pivot at point B. A spring of constant 400 Newton per meter and of unstretched length 150 millimeters is attached to the rod. as shown. Knowing that the rod is released from rest in the position showed, determine the angular velocity after it has rotated through 90 degrees. In case you were wondering, treat a rod like a bar.
One quick thing on there is that I didn't see it.
Yes.
I would have rotated 90 degrees with the.
So imagine that it kind of goes this way. Right, so here's the pin. It's going to rotate. As we go up.
Okay, yeah, go turn that button. I pressed the button, it was like saying, what's this? Push it out.
Oh, like go the other way?
Yeah.
Yeah, no. That'd be one hell of a spring, man.
That's really offset, otherwise I'm not going to do that.
Yeah, it's misleading the way that it's drawn, right? Because there's that what looks like the wall is there, so it looks like it's gonna collide. And I get that. It's just a misleading drawing. It's just to show you that that pin is fixed in space, right? That's really there to show us.
This is like,
Yeah.
And then the high was, is that out?
Plus. Yeah, take another couple minutes. Oh, I'm gonna go over it. Let's talk about it. Let's talk about it. What kind of problem do we have? What kind of problem? How are you going to solve this? Anyway. How are we going to solve this? What do you use? What's it asking for?
Angular velocity.
It's asking for angular velocity. We use Newton's law to find an angular velocity? No. So we have to use work energy, right? Because we haven't talked about impulse momentum. Okay. It's a work energy problem, right? Does it say anywhere in the problem statement that we have any friction or anything that's going to eat our lunch? No. So therefore, we can safely assume that we have no non-conservative forces. So we are just going to use conservation of energy to solve this problem, which means we need to understand two things. Well, it's four things. We need to know two things that break into four things. First is how much energy do I have to start with from this picture? And how much energy do I end up with in state two, right? And I know that I want this to rotate by 90 degrees. So the first thing I'm going to do is I'm going to draw this system, right? I'm going to draw this system in two states, like this. I probably could have drawn this better and bigger, but I didn't, and I apologize. All right, so what's going on here? Okay. You know what? I don't like how it's hard to see. Let's be quick. I'll do it again. So what do we have here, right? I've got state one, right? We've got point C up here. Point B is going to be here. We've got a center of gravity that's roughly there, right, with a weight pointing down. We're going to call this point A over here. I'm going to set my datum at point B. And point B, since it's a pin, will have BX and BY. I know this distance from point C down to B. This is 0.12 meters. The entire length of the bar is given as 0.60 meters. The distance here, therefore, has to be 0.30 meters. From point C, I have a spring attached here. I'm going to call this distance that the spring is actually deflected, I'm going to call that x1, right? And I also know that, and it's given on the bottom, but it could also be given here, this distance from B to D, right, was 0.35 meters. I know that the undeflected length of the spring is 0.15, and that's important, right? Because that suggests that in its free length, right, at 1.5, when that spring is at 0.15 meters, right, it's not storing any energy. But once we go beyond that, we're extending. And once we go below that, we are compressing, right? So this is state one. There's no velocities here, right? Everything starts at rest. And then we're going to have state two. It'll look like that, where everything is moved by 90 degrees now, right? And we still have those forces roughly. I'll put this here. Right, my weight is now pointing this way. I've got some velocity of the center of gravity there. I've got some omega 2 that's rotating with. This is point B, put point C right here, and that means our spring is now attached to point D here, right? Well, these 2 points, B to D, those were fixed. That length is not changing, right? They're both fixed to the wall. This is still 0.35 meters. This distance from here to here is still going to be 0.12 meters. So I can figure out what x2 happens to be. I think that, oh, there's one more, right? Let's do this. This is 300 meters. Okay, and those are my states 1 and 2, right? State 1, state 2. So we need to figure out some things. So let's talk about state 1 first, right? How much kinetic energy do I have in state 1? 0, right? Starts from rest, 0. Excellent. What about potential energy? Is it all in the spring? Where's my center of gravity as compared to my datum? Remember, my datum, it's hard to see in this picture, right? But it's up here at B, at least the way that I set it. You don't have to set it that way. You could have set your datum down here, right? And then it would be 0. You can set it wherever you want. It's completely arbitrary. I just picked it up there. So it's 0. It's not, the potential energy here is non-zero because I'm below the datum. And it's actually going to be a negative, right? Because I'm a distance below my datum. So remember, when we're tracking rigid bodies, we do all of the energy based off of the center of gravity. Okay? Do all of your potential energy calculations based off the center of gravity. So T is equal to 0. V1 is V elastic plus V gravitational, which is 1/2 kx1 squared. Where does this x1 distance come from? Excellent question. Well, look, this is the triangle that we made in this first. And this is just this triangle here. I know the distance of the bottom. I know the distance of the vertical leg. So I can figure out the hypotenuse here, right? This is just a right triangle. And here it is, right? So I just used Pythagorean theorem to figure out what x1 is. But it's not really x1. That's the total length that I've extended. So I have to subtract 0.15 from that to figure out what is my delta, right? How much have I stretched from the unstretched position? Which is why I get 0.37 minus 0.15 down here, right? Plus mgh, right? So plug in my things. I've got 1/2 400 times 0.37 minus 0.15. That gives me the total delta x, right? I square it, and I add 4 times 9.81 times negative 0.18 because I'm 180 millimeters below the datum. And I'll get 2.62 joules of energy in state 1. Then we can talk about state 2. In state 2, I've got kinetic energy both from translation and rotation. Right? And that's 1/2 mv squared plus 1/2 I omega squared, right? But just like we did in the last problem, we're not interested in V, we're interested in omega. So we're going to make our substitution of omega 2 times R. Right? I can plug all of my things in, and that's great. I'm going to leave it like this until I get to the final part of the equation where I plug everything back in. And then we can talk about potential energy at state 2. which is all in the spring this time. Like, again, right? Maybe it's not for you guys. Maybe you put your datum someplace else. And if you put your datum someplace else, that's fine. Right? That's fine. You could have started with 0 and had an increase in potential energy. It would have worked. But for my version, where I have my datum at the top there, now we're completely in line with that datum. Our H is 0. So we just have the elasticity of the spring, which gives me 1/2 times 400 times 0.2. Where does this 0.23 come from? If you drew it on the big diagram, this is just a cross-section or blowout section, right? From B to C was 0.12. From B to D was 0.35. So that means whatever's left over has to be 0.35 minus 0.12, which is 0.23 minus the free length squared. So I have 1.28 joules of energy due to my spring. So now we just do our conservation of energy equation, right? T1 plus V1 is equal to T2 plus V2. And here we are, right? Where T1 is 0. No V1, we calculated it as 2.62. Right, I can plug in all my things for my kinetic energy. So I have 1/2 times 4 times 0.18 V2 whole thing squared plus 1/2 times 0.12 omega 2 squared plus 0.1 plus 1.28. And I can solve for the angular velocity. Omega 2 is equal to 3.28 radians per second. That was fast. That was fast. We didn't have a lot of time.
What's state 2 again?
What's that?
State 2.
State 2 is when it's completely flat.
Well, like
All right, the state 2 equation is T2 plus V2. Right? So I get a number from here. But the rest of this, right, I just have to plug in my mass, my R, and my L. Which is all I did on the next slide. Just plug those in. Okay. Next week on Wednesday, we'll start talking about impulse and momentum. Okay. That's the plan. We'll tie that up. The next, I forget when the next exam is. We can talk about it later, but the stuff that's going to be on that's going to be impulse, momentum, work energy, and gyroscopic motion. I think next week we'll end up, well, depends because I thought we were going to get through a little bit more today, but that's fine because we talked about the CLCs, which I feel good about. I owe you guys some stuff on that too. Is there any other questions? Friend?
On the next slide, we finish state 2. Our next test is going to be like final with like all the topics.
No. Ain't nobody got time for that. Next test is going to be those three topics. I guess it's technically 2 topics because impulse, momentum, and work energy are in the same vein. Yeah, next time we'll do a couple problems. We'll talk about impulse, momentum, do some problems. We'll probably start impulse, or not impulse, we'll probably start gyroscopic motion when we get back from Thanksgiving. And then like week 14, wrap that up, have our test week 15, CLC stuff. That's the plan. Yeah, here's a concept quiz. We'll start class with this next time. Hold on one sec. There we go. Anybody wants to fill it out? Have a great weekend. I've got office hours from 3 to 5 if you want to come chat via Zoom. Not Monday morning, 9 to 11.